Alright, let's answer question 19 by hand. What would be the fidelity results for these two operators which differ only by global phase? So we have an operator made up of the x gate and another operator of the same x gate with e to the I over 2 as a global phase factor. So what are the state fidelity, average gate fidelity, and process fidelity results? Here, operator A is equal to the x gate. I'm just showing the matrices so you can see them visually. And let's analyze the probability amplitudes if they affect the measurement results when having a global phase factor. So given a global phase factor of A plus IB, if it was in this form, which is any complex number, since we measure the square of the probability amplitudes, then we will see that any imaginary unit part goes away. A squared plus IB, A minus IB, A minus I squared, B squared. So we see this goes to 0, and this negative I squared is equal to negative 1, and negative that is going to be positive, and so it becomes a real number with no imaginary part. And more concretely, if the complex amplitude was in the form e to the I theta, then the absolute value of the complex number squared would equal itself times its conjugate, which is e to the negative I theta, and there we can see clearly that it goes to 1. So there'd be no relative difference in the measured results. So phase doesn't affect measurement, but will it affect the fidelity between these two operators in the middle of the program? Well, let's see. The state fidelity is defined to be between a sigma and a rho equal to the trace of the square root of rho, or whichever one you want, times sigma times the square root of rho, or vice versa, and all of that squared. But this requires rho and sigma to be density matrices because they have to be valid quantum states. If they're not valid quantum states, then there's no state fidelity. And the Pauli matrices, like the x gate and y gate and z gate, are not valid density matrices, nor are they valid state vectors, because their trace does not sum to 1. The trace of a density matrix must equal 1, but the trace of the x gate is equal to 0 because its eigenvalues is equal to plus or minus 1. So the state fidelity doesn't apply here, and that already gives away the answer. Because each of these have state fidelity in it, but that doesn't even exist, so we can't use that. So answer C is the right answer. But let's be assured that is the right answer by making sure average gate and process fidelity are 1. The process fidelity is the fidelity between a noisy channel, epsilon, and a unitary, u. And so that unitary is our target. And so we need to compute the super operator for each of those matrices. And the super operator for u and epsilon is given below, which I'll show you. But d is going to be the dimension, which is going to equal 2 since we have a square matrix. The dimension is 2 for the x gate. So the super operator for epsilon, the noisy channel, happened to be the same as the super operator for the unitary in the definition. And so since they are the same, we can solve this more clearly the fidelity of the process between epsilon and u is equal to the trace of its superoperator divided dimension squared, and the trace for the adjoint of S sub u is going to equal itself, since it has elements off the main diagonal that are all just real numbers. And remember, S sub u and S sub epsilon are the same. So this really is S sub u squared, which is going to be the identity matrix. And the trace of an identity matrix is equal to its dimension, which this is a 4x4 superoperator. So the identity matrix is going to be a 4x4, and we get 4 over 2 squared, which is equal to 1. So the average gate fidelity is equal to this crazy integral, or if we have the fidelity of the process, it's equal to 2 times the fidelity of the process, the dimension, times the fidelity of the process, plus 1 times the dimension, which is 2 plus 1. And that equals 3. So there we go. 3 over 3 is 1. And we verify that C is the correct answer.